So we talked about using derives to find roots of complex numbers. Now we're looking at some very specific ones, and it's what we call the roots of unity. So solving z to the power of n is equal to either 1 or negative 1. So the modulus is 1, so unity. If we were to put all the solutions on the Argand diagram, what we've seen is they're going to be symmetric. But because the modulus of all these is going to be 1, they'll all lie on the unit circle. So it'll be on that specific one. And if you were to join them up, because they are symmetric, you'll get a regular polygon. So let's look at the fifth roots of unity. Z to the power of 5 is equal to 1. And, well, the nice thing about the unity ones, we know the argument of 1 is 0. And if it was negative 1, it'll just be pi. So it makes the equation here nice and easy. I put plus 0 there. The reality is it's just 2 pi k, of course, because plus 0. It's the fifth roots of unity. And because we're talking about real numbers, I can look at them in conjugate pairs, so I'm going with 0, plus or minus 1, plus or minus 2. So we end up with, it says 0, 2 pi and 5, its conjugate, negative 2 pi and 5, 4 pi and 5, its conjugate, negative 4 pi and 5. If I was to place it on the Argand diagram, there's the first solution there, it says 0. The next one, 2 pi and 5, its conjugate, there's 4 pi and 5 and its conjugate, and sure enough, it is a pentagon sitting on the unit circle. Some common sorts of things that get asked with the roots of unity. It starts off, just says omega is a complex root of the roots of unity z to the power of 5. Well, they've written it as z to the power of 5 minus 1 equals 0, but it is, of course, the same equation. Show that omega squared, cubed, power of 4, power of 5 would be the other roots. Important thing to note here, when they say a complex root, it's probably more correct, because what they're really talking about is a non-real root. Because if they were to choose the real root, which is 1, well then 1 squared's 1, 1 cubed's 1, 1 to the power of 4 is 1, 1 to the power of 5 is 1. You'd only ever get that one solution, you wouldn't get all the other ones. So we're really talking about one of the non-real roots. So we know z to the power of 5 is equal to 1. Omega we're told is a solution, so we know that when we raise it to the power of 5, it's equal to 1. Well, a bit of manipulation of index laws, I can show the other ones are also solutions. See, I could raise omega to the power of 5 to the power of 5. And that would be 1 to the power of 5, which is 1. So omega to the power of 5 must also be a solution, because it satisfies z to the power of 5 is equal to 1. I could do this. I could say, well, omega squared to the power of 5 is the same as omega to the power of 5 squared. And omega to the power of 5 we know is 1. 1 squared is 1. Oh look, omega squared is a solution. I could then go, well, omega cubed to the power of 5 is the same as omega to the power of 5 cubed. And omega to the power of 5 is 1. 1 cubed is 1. Omega cubed is a solution. No surprises for guessing what I now do. I could do the same with omega to the power of 4 and show that that is also a solution. That's a long way around it. A quicker way of doing that is to do it like this. Alright, we know z to the power of 5 is equal to 1, so we still say yes, that means omega to the power of 5 must equal 1, because we know omega is a solution. We still do that. But instead of playing around with omega squared, cubed and 4, I just go omega to the power of k, where k is some integer. I could always rewrite that to be omega to the power of 5 to the power of k, which becomes 1 to the power of k. Well, 1 to the power of anything is 1. Now, actually, not only is omega squared a solution, cubed, 4, 5, any power at all will always be a solution to this equation. It's just we only picked 5 of them because it was a pentic equation. I only wanted 5 solutions. But all the others would be solutions as well. Something to note. Z times Z conjugate will always equal 1. Why? Well, remember, Z times Z conjugate is the modulus squared. And we're talking about something that sits on the unit circle. The modulus is 1. So for roots of unity, a number and its conjugate will always equal 1. Now here we go. Z is equal to omega to the power of k. The conjugate would therefore be omega to the power of n minus k is what I'm saying. If omega was, say it was that first one, it's just 2 pi and 5. Let's have a look at the positioning. We know the solutions. 2 pi and 5 is up here. Omega squared would become cis 4 pi and 5. So it would be this one over here. Omega cubed becomes cis of minus 4 pi and 5. omega to the power of 4 is cis minus 2 pi and 5, and then obviously omega to the power of 5 is equal to 1, cis 0. But have a look. Omega squared, omega cubed. Yes, they multiply together to give omega to the power of 5. So the powers add up to be 5. Omega, omega to the power of 4. So our conjugates are when the two powers add up to be 5. They'll be the pairing. Now you don't have to pick. It says you can pick any of them. Imagine if I picked minus 4 pi and 5 as the first one. So there's our first one, minus 4 pi and 5. If I was to square that, I would end up over here at cis 2 pi and 5. Right? If I was to double that argument, I'd end up at cis 2 pi and 5. There's omega squared. If I was to go round another 4 pi and 5, I'd end up down there at cis minus 2 pi and 5. That would be omega cubed. And if I was to go round again, I get cis 4 pi and 5. Yes, they're in different positions, but you can still see that the conjugates, the powers, are adding up to be 5. It doesn't matter which one you pick, as long as you don't pick the real one, that will always happen. All right, another very common question. It's one of these ones where we can quote it, and they say ask us to prove it. And very often they do. So how would I prove then, for the fifth roots of unity, that 1 plus omega squared plus omega cubed plus omega to the power of 4, if I was to add up all these things, I'd get 0. Well, I could do it this way. I could say I know that omega squared, cubed, 4 and 5 are the 5 roots. The sum of the roots of this equation would be minus b on a. And if we look at the equation, well, b is 0. There is no coefficient of z to the power of 4. So yes, they must equal 0, but also noting, but also omega to the power of 5, I know, is equal to 1. So yes, I get all of these things add up to be 0. That's one way I could do it. I could use this idea. All right, here's the equation, omega to the power of 5 minus 1 equals 0. But we know how to factorise that. Omega to the power of n minus 1 will always be omega minus 1, and then we get 1 plus omega squared plus all the way up to the power of 1 less. Well, have a look at this. We've got two factors that multiply together to give 0. We know one of those factors must be 0. However, the first one can't be 0. Remember, we specified that omega was not the solution 1. Therefore, we won't get 1 minus 1, right? Because omega can't equal 1. It wasn't the real solution. It's one of the other ones. Therefore, if that first factor can't equal 0, it must be the second factor that's equal to 0. Again, we've proven that result. Or, how about we do it this way? This is what I'm trying to show is equal to 0, but look at it. It's a geometric progression. I could say, well, the first term's 1. The ratio is omega, the number of terms is 5. Plug it into our formula. Well, hang on, r to the power of n becomes omega to the power of 5 minus 1. Well, that's what we said was equal to 0. There's a third way of doing it. And I suppose if you go back to the diagram, what we're basically saying is if I was to make those all vectors and I was to join them all together, I will end up landing at 0. I guess that's a fourth way of doing it. You could use vectors to do it as well. That's probably rare doing it that way, but it works. So pretty much in roots of unity, there's only two things we know. Omega, in this case I'm talking about the fifth roots of unity, omega to the power of 5 is equal to 1, and the other one is that 1 plus omega squared and so on is equal to 0. With those two things, I should be able to solve all sorts of problems. We're going to find the quadratic equation whose roots are omega plus omega to the power of 4, and the other root is omega squared plus omega cubed. Okay? It's a quadratic. The sum of the roots then, so the middle term is what we're looking at, would be those 4 added together. But we know 1 plus omega squared plus omega cubed plus omega to the power of 4 is equal to 0. Therefore, this expression must equal negative 1. Okay, I've got the sum of the roots. Product of the roots. Well, if I was going to expand that out, oh, hang on though. Power of 6 and power of 7. Well, that's all right, because I know omega to the power of 5 is equal to 1. So I can rewrite that as omega plus omega squared. I actually end up with the same expression, which I know is equal to negative 1. Right? That's what I say. Any power is going to be a solution. Omega to the power of 6 is still one of the roots. It's just written differently, because omega to the power of 6 is the same as omega. Let's form our quadratic. we know it'll be x squared minus the sum of the roots, so it becomes plus x, plus the product of the roots, minus 1 equals 0. That's the equation that would have those two things as the solution. This time we're going to play with cube roots of unity. And they've actually told us, look, use the fact 1 plus omega squared is equal to 0. All right, we don't have to go and prove it. That's the fact. And the other fact we know for this one is omega cubed is equal to 1. What would 1 plus omega squared to the power of 3 equal? You could expand the whole thing out, I suppose. Let's use the fact that 1 plus omega squared is equal to 0. I can make this much easier for myself by changing 1 plus omega squared to be minus omega. And then I'm just cubing a single thing. That's minus omega cubed, and we know omega cubed is equal to 1. It's negative 1. Algebraic fraction question. Yep, I could get a common denominator and do all that, but again, because I'm dealing with cube roots of unity, I can play around with these denominators. Instead of having two terms on the bottom, end up with one term on the bottom, because 1 plus omega must be minus omega squared, and 1 plus omega squared must be minus omega. That's an easier fraction to play with. Common denominator becomes omega squared. On the top I get minus 1 minus omega, but now I can play around with that and turn that into omega squared. I've just ended up with omega squared on omega squared, which is equal to 1. We're going to create a cubic equation. These are our three solutions. 1 plus omega, and 1 plus omega squared. Well, that means it must factorise. They've told me 1's a factor, so I know z minus 1. The other factor must be a quadratic with these two roots. So I'll write it as z squared minus the sum of the roots, 2 plus omega squared, plus the product of the roots, 1 plus omega squared plus omega cubed. Well, I could have probably simplified that down as well, because the 1 plus omega I could have turned into minus omega squared. Let's play with those. Actually, I've just got that down. Because look, 2 plus omega squared would be 1 plus omega squared, which we know is 0. So I just get 1. And in the product of the roots, 1 plus omega squared, that's equal to 0. Omega cubed, that's equal to 1. So I have the second factor. Let's expand it out so it looks like a nice cubic equation rather than a factorised one. That tidies up a bit more as well. There's the equation. Z cubed minus 2z squared plus 2z minus 1 is equal to 0. Ooh, we're going to solve this equation. Now, when you look at the pattern in the equation, this lends itself to using roots of unity, because all the coefficients are 1, but also it's that nice pattern, power 5, power 4. It's basically, I know that. If it was the sixth roots of unity, I know it would be factorising to be z minus 1 times that expression that I've got up there. And finding the sixth roots of unity is easy. Finding the solutions to that equation, it's a pentic, is not easy. So let's do the easy one. I'm going to change the question, because as I'm saying, I know I can find the sixth roots of unity. It'll be 2 pi k on 6, where k is 0, plus or minus 1, plus or minus 2 and 3. I've got those 6 solutions. I know the answers to that equation, but I want the answers to this equation. Right? We change it into something we can do. How do I do that? I'll multiply top and bottom by z minus 1. Now, if you've got a fraction equaling 0, it must be the top of the fraction equals 0. So the bottom becomes irrelevant. So we have the top. So I know, hang on, I'm going to get the 6 roots of unity, but the one solution that I don't want is z equals 1. I don't want that solution, because that would create a situation where I'd have 0 on the bottom of the fraction. Therefore, the other 5 solutions must be the solution to my equation. So there they are. And in this case, their exact values, we can work those out. There we go. We end up with half plus root 3 on 2i, half minus root 3 and 2i, and so on. There are the 5 solutions. Start off with a very old HSC question. The 9th roots of unity they're talking about here. And they've told us specifically which one to pick. So we're going to let omega be the very first one as we're going around the circle. Cos 2 pi on 9 plus I sine 2 pi on 9. And then say, hey, show that it doesn't matter what the power is, it's always going to be a solution. So that idea, right? Z to the power of 9 is equal to 1. They say, well, yes, if I was going to solve this, I didn't actually bother with the plus or minus on this one because I just wanted to highlight that any power could be a solution. So I just stuck with all the positives. Doesn't really matter. But 0, 1, 2 going up to 8. Well, using Demoivre's, I can say that's the same as cis 2 pi on 9 to the power of k. That leaves me with omega to the power of k. So there it is. Omega to the power of k is always going to be a solution regardless of the power. All right. Then it came with this, which is that basic question, but written slightly different. Instead of saying 1 plus equals 0, they've moved the 1 to the other side. But that's all they're really asking here. How did I choose to do it? I went with sum of the roots. So I'm just going, oh, well, sum of the roots is equal to 0, so that's true. I'll move the 1 to the other side. I've got that all equals -1. Hence show cos of pi on 9 times cos of 2 pi on 9 times cos of 4 pi on 9 is 1 on 8. I've found all the roots. So I'm going to factorise z to the power of 9 minus 1. But you'll notice the way I've grouped them. I've grouped them so the factors with the conjugates are next to each other. Z minus 1, well, that one I knew because it's the roots of unity. Z minus 1's got to be a factor. Z minus W, but instead of writing Z minus W squared, I wrote to the power of 8 next, because they will be the two conjugates. Then did the squared and 7, the cube and the 6, the 4 and the 5. Because when I expand these two factors, the W and the W to the power of 8, I'll create a quadratic. That quadratic will be minus the sum of the roots. If I add conjugates together, I get twice the real part. So I end up with twice the cosine of 2 pi on 9, and obviously z, plus the product of the roots, z times z conjugate, that equals 1. And I do that for each of those pairings. That can be tied up a little bit more because we know the cos of 6 pi on 9, because that simplifies down to be, what is it, 2 pi on 3, which is one of our exact values. So there's that factor z squared plus z plus 1. And I'm left with, you'll notice, 3 things that involve cosine in factors. In other words, they're multiplied together. And look at what we're trying to show. 3 cosines multiplied together. So what would be really nice is if inside these factors I didn't have the z squared and the plus 1, because then I'd be going cos times cos times cos, which is what I want. How do I get rid of the z squared plus 1? I want to make that equal to 0. Well, how do I make z squared plus 1 equal to 0? I'll let z equal I, and then that becomes 0. Here's my new expression. The left-hand side becomes I to the power of 9 minus 1. The right-hand side, I minus 1. But then those 3 factors that involve cos have a single term involving cos. We should now be able to play around with this and get our results. I want the causes. I don't want the I there. So I factorised out the I's, if you like. So that's I times I times I times I. So that's I to the power of 4 that I've pulled out. I've also pulled out those negative signs. So negative times negative times negative. There's the negative. I don't know why I didn't pull out the 2. No, I should have. But anyway, it doesn't matter. We'll do that later. But now I've got a common factor on both sides of I minus 1. Well, I know that can't equal 0, so I can divide both sides by the I minus 1. Minus I to the power of 4 is -1, so I divide both sides by -1 as well. And now I've pulled the 2's out. 2 times 2 times 2 is 8. All right, we're very close. But our question didn't have cos of 8 pi on 9, it had cos of pi on 9. 8 pi on 9. We're in the second quadrant. The acute angle would be pi on 9. So cos of 8 pi on 9 is the same as minus the cos of pi on 9. Now let's pull out that -1, divide both sides by 8. We've proven our result. So we eventually get there. Let's do some more recent ones. 2022, it was the fifth roots of unity they asked us to look at. Solve the equation by first finding, and this is where you've got to be careful because it's not, in this case, z to the power of 5 equals 1, it's the negative 1 case. So z to the power of 5 is negative 1. Well, this time then, I'll get pi plus 2 pi k on 5 to create my 5 solutions. And so there are my 5. I might have been a bit lazy there by making it cis plus or minus pi on 5. I probably really should have written it as cos pi on 5 plus I sine pi on 5, and then cos of minus pi on 5 plus I sine. But anyway, there's our 5 solutions. Show that if z is a solution, so one of those solutions that we just found, but not the one where z equals negative 1, then u equals z plus 1 on z is a solution to this quadratic equation. Well, let's investigate. I want to show that it's a solution. Show that, easiest way of doing it, I'll substitute in. So if I substitute that into u squared minus u minus 1, I end up with z squared plus 2 plus 1 on z squared minus z minus 1 on z minus 1. Hang on, I can play around with that. 1 on z squared will be minus z cubed. So that's using the fact basically z to the power of 5 is negative 1. Because that's the other way of thinking about it. I'm saying, hey, I'm just going to multiply by z to the power of 5. Oh, and of course 2 minus 1 is 1. So I have that. But they are the fifth roots of unity. I use this idea again. Multiply top and bottom by z plus 1. Because remember, I'm saying z can't be negative 1. So okay, I can multiply top and bottom by z plus 1. So now I've got z to the power of 5 plus 1 on z plus 1. Okay, we're getting there. And that is equal to 0. Because z to the power of 5 plus 1 is equal to 0. We got there, but we've shown that yes, z plus 1 on z is a solution to this quadratic equation. Hence find the exact value of cos 3 pi on 5. 3 pi on 5. That was one of our solutions. Well, one of our solutions involved cos 3 pi on 5. One of them was cos 3 pi on 5 plus I sine 3 pi on 5. So why don't I let z equal that particular one? That means z plus 1 on z will become 2 cos 3 pi on 5. And that's good because we want to find cos 3 pi on 5. But we also now know that z plus 1 on z is a solution to this quadratic. And I can find the solutions to that quadratic. It's 1 plus or minus root 5 on 2. What that's now telling me is that 2 cos 3 pi on 5 must be one of those answers. It's got to be one of them. The question is which one? Well, what I do know is the cos of 3 pi on 5 is a negative number. So it can't be 1 plus root 5 on 2. Well, that means it's got to be 1 minus root 5 on 2. The only thing we've got to do now is divide both sides by 2, and we've got our answer. Something to note about the picture with the negative roots of unity. The roots are positioned like this. So negative 1 was the real one. We're still going to get that pentagon. They're the 5 solutions. If cis pi on 5 is omega, minus omega squared is here at minus 3 pi on 5. Right? Think about it. Cis pi on 5, to get omega squared you double the angle. So you get cis 4 pi on 5. To get the negative you would reflect through the origin. So you'll end up at cis minus 3 pi on 5 when you do that reflection. Omega cubed, well that'll be over at 3 pi on 5. But then minus omega to the power of 4 will be over here. But again, look at the conjugates. 2, 3. The powers 2 and 3 add up to 5. 1 and 4 add up to 5. That pattern's still there. Oh, and of course omega to the power of 5 is sitting over there at negative 1. The other thing to watch out for is the sum of the roots idea. Okay. It's now not going to be 1 plus, it's going to alternate. So in this case, the sum of the roots, because there's the roots, omega minus omega squared, omega cubed minus omega to the power of 4. So those sum of the roots, they'll still be 0, but we'll end up with this expression instead, which makes sense because if we do it by the factorization way, well, that's our factorization for w to the power of 5 plus 1. The second factor now, the signs are alternating in that factor. That's why that is equal to 0. So 3C will do.